All right, let's talk about things. Yeah.
I think we have like the same problem, but you definitely have looked into it more than I have, so I'll let you.
Okay, my remote desktop connection just disconnected on the original that. Okay, so starting with problem one,
Okay.
it's the I-motional current over ignoring electrostatic contraction.
Okay.
So the equation I used for the DC, I think you mentioned in last class period, you used epsilon A times that on the equation as if it was a transverse Ohm drive.
That's not for a transverse comb drive. So what I'm saying is, I mean, it may happen to work out to be the same thing, but that's not why I'm using that equation. Okay. So we have our bias voltage up top. And then we have two capacitors. Connected in parallel. This one over here on the left, let's say, represents what happens when the Coriolis force is pushing one of the masses up. So it's going to have EA over D plus XS. Let me write that better. And this one over here is going to have a capacitance of EA over D minus XS. So this is just simple parallel plate capacitors where there is some amount of displacement. And I'm actually going to call this D naught, representing the unbiased capacitance. So neglecting just electrostatic forces. Okay.
Okay, that makes sense because the equation I saw, to me, it's like that's the intrinsic drive equation. No, it's because it's two parallel plates. That's
Two parallel plate capacitors in parallel. So C is just these two things added together. Epsilon A over D naught plus XS plus epsilon A over D naught minus XS, which is epsilon A times 1 over D naught plus 1 over D naught minus.
this would be your C, or no, this is your C. Your C naught would just be
Twice epsilon A over D.
that's what.
Yeah. So this is C as a function of XS, since that's the only variable here. So when we take the derivative of this with respect to XS, that's when we get the I might have gotten the signs wrong here, but whatever I told you the other day. I can throw it into the online derivative calculator I used again because I was too lazy to remember how to do this.
Oh, that's what they're there for.
That's not. So.
Trying to connect to my remote desktop, which has a Mapcat on it. That's behaving weird. Okay, so that's the correct equation used for DCEX, and it gives you C, so you can find change in capacitance. For XD,
What is XD?
the displacement of your drive.
Okay, yeah,
Right, so for that, I took VAC is 1.5, because
Uh-huh.
it's at peak cosine of 0. And then VDC is much greater than VAC, 5 volts greater than 1.5 volts. So
Okay.
I use the form VDC, VAC, DC, DX, which is going to be this one.
no,
It's not.
no,
No, you're right, because that's
because this is only for the sense.
Okay, I'm saying wrong what I'm doing here correctly, which is that's the number of fingers times epsilon A over.
It should be exactly what we did in the example problem,
It is.
because it's exactly the same thing as the example problem, except the number of fingers is and the parameters are different for the
Right,
drive mode displacement.
Okay,
so that's 2 ND, the number.
that was, I was like, I know I made notes earlier pointing to stuff, and that was my question was. Our capacitance and our.
So our drive mode
DCBX
capacity,
is different.
Yeah.
Because we're not dealing with the transverse column drive.
right,
Okay,
everything else is
that
the
I can
same,
do,
yes,
but I did want to go down a rabbit hole. I was like, I'm not doing clearly anyway, let me just double check.
yeah.
Okay,
So for the drive mode, it's effectively the exact same thing as we did with the example problem. We have a longitudinal comb drive that we are exciting using a small AC drive signal, causing it to vibrate back and forth, and let's call it the X direction. Our rotation is occurring in the Y direction, and so we're getting a plate displacement in the Z direction. So all this stuff right here is for that Z direction. All of this is for the sense mode stuff,
yes.
right?
No, I think the only thing that might be different is FAC, multiplying that by 2, because we have 2 drive mode actuators.
Mhm.
So that'd be 8 times VDC, VAC.
Well, so, but I want to be clear here. There's a comb drive actuator on the left, and there's a comb drive actuator on the right per proof mass. So you should not effectively multiply it by 4 because there are 2 proof masses, because each one is only going to displace 1 XD, which is in turn only going to cause 1 displacement, except 1 in the up direction and 1 in the down direction.
So we're still good at 2.
Yes,
Okay, yes, okay, because we're different directions, same plane, but it's still just 2 sensing mechanisms.
yes.
Okay, so that should be 4 then instead of 8.
Yeah,
Yeah.
so we should have like 4 times VDC times VAC times capacitance stuff.
Yeah.
In which we need our sense mode displacement to calculate.
You don't need the sense mode displacement to calculate the drive mode displacement. You need the frequency, maybe. Let me go get my notes.
Okay. I just say that because let me make sure I'm looking at something. See this? This is how I took the notes of it. And this is that you were just doing, I think, right?
Right, I did 8 by mistake, because I was thinking because there's 2
Yeah,
there, but.
That's fine, but to calculate that, our drive mode displacement, we have to have that force, right? Our
Right,
sense
which,
force.
yeah, that gives
But
you drive
remember-
mode displacement.
But when we have our C, this one works out to where it's not a function of.
Right, because it's DC, DX. So,
Yeah, but what we just did was, this, which is a function of,
that's only for your eye motional current sensitivity. That's for this right here. So this DC, DZ, I was using this form, that's incorrect. The correct form is the one you just showed. That's for your sensitivity.
Yeah.
Or that's not exactly sensitivity, it's your change capacitance with respect to.
but here, that's what I calculated the same thing. Or that's what I took the note as, was that. when we
Right,
take-
but that was a different system. That's a,
Or-
no, it's okay. It's not a parallel plate, this is a longitudinal cone drive, I'm sorry, the sense mode,
Yeah.
transfers cone drive, that's why.
Well, should I take the derivative of it? And that's I don't know, it'll come back with
Or
make it feel stupid.
I'm already feeling very stupid. Epsilon naught HD over DD. Okay, now for this, it's going to be epsilon naught.
Yeah, actually.
S times W sub S. That's epsilon area.
Have the,
Times
is DX D actually maybe?
one.
No, that doesn't make sense.
E. Yes.
So when we did our example problem,
Mhm.
we're calculating the drive time displacement
Mhm.
for the function of the AC force calculation.
Yes.
Which is in this case, it was 2 times DC voltage, AC voltage, and DC DX.
Right.
Which in this case works out to not, that DC DX is not a function of X, because we end up with number of fingers times, we get N times epsilon.
So there's a longitudinal cone, right? So let me write this down. The drive system, right? Our capacitance, let's call this CD as a function of X. So there's going to be epsilon. So let's look at what quantities that we have here, right? So the epsilon is obvious, and then the displacement or the gap between our things. So let's see, I give you a height and an area of overlap. So HD times LD plus XD. Because as our drive mode displacement occurs, we are increasing the area of overlap by increasing the length of the overlap, right? And then, so this is this capacitance of 1 finger overlap
Times N.
times 2N, because,
Yeah.
right. So I would argue very much that this is a function of XD, and
Yes.
therefore you can take a derivative of it.
The way that I took the notes, so I don't know why I did. I think I might have actually written that subscript down, which might have really screwed with me. I didn't put a subscript on it, which I don't know.
So if we take the derivative of this thing, that's just going to be twice N epsilon HD over DD. Right, because the derivative of XD with respect to XD is just a 1.
Mhm.
So from here, I'm going to call this FD for our drive mode force, right?
Mhm.
So our drive mode force, let me go back here.
220.
So 1/2 twice VDC, VAC, cosine omega naught D T, because we know that we should, our excitation frequency should be the resonant frequency of the drive mode to get the largest possible amplitude, which I didn't say, we talked about that in class, but nowhere in the problem statement did I tell you what frequency we're at.
That was another question.
Yep.
Very good.
Times D CD EXD. So the magnitude of our displacement force effectively just means we're going to throw away the cosine bit because we don't care about what it's doing as a function of time. We only want the maximum value, right? So we have 1/2 times 2 gives us 1. So that is going to be VDC, VAC, and then we multiply by the DCD by DX. So that's going to be twice N epsilon H sub D over D sub D. And then because there are two actuators, actually, I'm going to cheat and call this E for electrostatic force. I'm going to call this D is just twice the magnitude of F. Yeah, so it should be 4.
You mind if I show you what I calculated here on MathCAD just for my emotional current? I got all the steps here.
Sure, what'd you get?
I got 7.45 times 10 to the negative 10 with a 9-degree.
So your motional current, I'm concerned about the phase angle. So when I calculated mine, I simply used, here's why to me, the phase angle doesn't make any sense, right? So the phase angle is representing the delay between, what's going on between the drive and the sense vibrations and all of that kind of stuff, as well as the acceleration. I looked at it as a function of amplitude, right? I'm not really looking at phase angle. So when I did this thing, my sense mode displacement definitely has a J in there, but when I calculate my motional current, this XS is simply the magnitude. Because I don't care about when it's displacing by that amount. I just I care about the total displacement.
Right, and I did take the magnitude here. I noticed though for my velocity term, 1J omega naught D, actually that should be omega naught S.
They're the same thing.
I did the magnitude of excess. So if I remove that, I get 7.451 times 10 to the negative 10 with a 180-degree angle. But
so it looks like in my solution here, I forgot one factor of 2. So I got 18.81 nanoamps. But I forgot a factor of 2, which means this should be 37.
Ish.
Yeah.
6.2.
Okay, so we got the same thing for that and that. I forgot a factor of 2 there. $132. That seems like yours is double mine. I was just looking at the exponents because I have mine expressed in nanonewtons, and you have yours expressed in 10⁻⁷ newtons, but that should all.
Well, for whatever reason, my version of MathCAD doesn't like nanonewtons.
Yeah,
You can do.
well, I have 10⁻⁹.
Oh, okay,
Goes to powers of 3.
okay, that's better.
So your drive mode displacement is twice as large as mine, which makes perfect sense. If your drive mode displacement is twice as large as mine, then your sense mode displacement should be twice as large as mine. Your sense mode displacement, you get to be 0.6 microns, and I got 1.2 microns.
Which is exactly double.
But it should be the other way around because my XD is half as large as it needs to be. So. -2 MD over MS XD omega QS over omega naught S. So. Explain what that 2 is doing there. In the front of your motional current.
And maybe there because I originally wrote this thinking that there are two parallel plates here, but if we have the two here, that,
Yeah,
yeah, that already took account of that. So I fixed that and then would have changed that too.
right. So you're still looking at 0.3 now. I said AS, let me see. 500 times 200, yeah, so you just did that separately. So everything that you're doing seems perfectly correct to me. The only thing that I am confused on, and this was my math CAD just being weird the other day as well. Why, like I understand. I wonder why your value is half as large as mine when I think it should be twice as large as mine. So is mine wrong or is yours wrong using the exact same relationships?
Well, I do think it should be twice as large.
So I mean, if XD, like this is a linear function of XD, right? So if this is XD, if your XD is twice as large as mine, then your XS should be twice as large as mine. My XS is 1.244 microns. Scroll up.
Sorry, this is on it.
Yeah, it can't do it for whatever dumb reason. Okay. So our Q's are the same. MD is 200. MD is, yep. HD is 10 microns. LD is 50 microns. DD is 2 microns. DS not is 5 microns. 1.25. BDC is 5. BAC is 1.5.
Yeah, it's 1 radian per second in the problem statement.
So, okay, so here's,
Yeah, it's spotted it.
yeah. And that was me figuring out what's going to make that. Like, that's the answer to the last part. Okay, so that seems fine.
Okay.
Yep.
Thank you. It's
Yep, no problem. Yep. My rotational rate is the rotational rate that makes it hit the threshold for pull-in. That's what it is. Okay. You didn't see that.
No, I didn't. And honestly, I'm not gonna remember it too well. My no is going to be about problems too, because if I've made the errors I made on problem 1, I probably did problem 2 incorrectly.
Yeah. So for problem 2, it's the sense mode part that is going to have pull-in effects that need to be determined, right?
Right, and the way I handled that in my very sleep deprived mind was using the equation for, when you have electrostatic actuator. The
Parallel
equation-
plate, electrostatic actuator with pulling, the exact equation that you used for the homework that we were talking about the other day.
Right. In that equation, I rewrite it as a third order polynomial where the x we're trying to solve for is XS or magnitude of XS. And then use epsilon LS omega S over 2 KS for our capacitance there, V bias squared, and then I get 3 solutions for that polynomial. Then I find what your pulling voltage is. And using the equation for C naught to epsilon LS omega S over DSO. Although I don't think I'm taking into account correctly that this is 2 capacitors here.
But no, there are 2 identical capacitors. Each one is going to have the same pull in.
Oh, okay, so yes, there's 2 epsilon, yeah, okay, that's the point. I get what my point is, which is larger than my V bias, which means that my solution for that polynomial has to be less than the pull-in, which is 1.667 micrometers, and it has to be less than the gap, so I get 0.423 micrometers.
That's exactly what I got, just as a heads up.
Okay, and then there was for the I motional current, what I did is, including this electrostatic force, there were 2 approaches. One, I don't think this is right, where I just took this value and substituted it into the equation for my displacement.
That is exactly what I did.
Okay, so you're
Because-
not adding this to your initial displacement.
No. So I'm just saying this is what the new gap is, because we're saying that we have some steady state DC attraction between these 2, and then you're vibrating around that point.
Okay. Just make sure I got this correct.
Which should follow very closely or exactly what we did the other day.
Yeah.
One of the homework problems.
Now, one thing that I didn't really think about when I did this is that it's going,
closer.
yeah, so I took into account the effect that it's going to have on the sense mode, but I didn't take into account the fact that it's going to change the drive mode force a little bit, because the area of over the height,
It's gonna,
the
yeah, okay.
height
yeah.
changes slightly.
Okay.
I guess you can't really compensate for, I was just trying to think of like compensation for that, but you can't
If it,
mechanically compensate for that.
no. Not if your plate and the fingers for the drive mode are rigid structures,
Yeah,
no.
it's not, yeah, okay. I was. my brain-
Okay, so plugging in excess, just ignoring this note I made for myself, because I thought I was doing something different. I'm getting for my motional current 1.818 times 10 to the negative 10 at 90 degrees angle.
Mhm.
Let me change that to the inch.
Yeah.
Or 181.833 femtoamps.
Yeah. Oh. Okay. And 5 amps.
Times 10 to the negative 12.
That's Pico.
Yeah, I was like, I don't think that's right. 15.
I swear I belong in this.
That's okay, you know what femto is, that.
Yeah, okay.
So what Sam and I were just talking about, and I neglected to do this in my quick and dirty solution to make sure I gave you guys enough information, is the fact that effectively you have your drive mode actuator, and then your plate. Well, the electrostatic attraction between the plate and the substrate is going to cause your fingers to drop a little bit, which is in turn going to change the force by some small amount, right? Because HD is no longer 10 microns. It's going to be 10 microns minus that displacement.
Okay, so need to recalculate FAC, figure out.
Yeah.
Okay,
If you want to be thorough, which again, I'm perfectly honest here. I did not think about that effect when I was writing this, but that absolutely is going to cause some small change.
Well, in this case, we're using the electrostatic force, FAC, I'm just calling it that, or FD, or whatever you want to call it.
Right,
We're using that to then solve for what our drive displacement is, then get our sense mode displacement.
right.
Well, if we're calculating out here, including the pulling effect.
So I'm not saying we need to determine what the effect of the sense mode is going to have on that. What I'm saying is that DC attraction between those two plates is going to cause the height of the overlap in the drive mode to change on a DC level, which is in turn going to change the electrostatic force of the drive mode as well. So like we have to be careful about which electrostatic forces we're talking about, because we have an electrostatic force in the X direction for the drive mode and an electrostatic force in the Z direction.
Okay, so if I wanted to go into extra detail here, I can then recalculate what that drive mode displacement is due to this.
Right.
Now change 10
Right.
micrograms minus your excess that we just calculated.
Yeah, and so honestly, it should just be. So for your FAC equation, HD becomes HD minus that equilibrium displacement that you're seeing in the Z direction. So if we had 10 microns originally, and now we have 10 minus, let's just call it half a micron for the sake of math's sake, then the force is going to be, let's see, half a micron would be 5% of the total displacement. So the force should be 95% of what its original value is, ballpark. If the force is 95% of its original value, then the drive mode displacement is 95% of its original value, which means the sense mode is exactly right, because we used matched modes. So it's not like an insurmountable thing to take into account.
So I think I've got problem one, the mistakes I was making, which were numerous. Problem two, I think I'll go ahead and I've written out a note for myself to update this map and figure out what that new displacement is, because that's actually kind of interesting. And did my emotional current sound kind of in the ballpark?
I have no idea because I have the wrong angular frequency, but I mean, the equation for the motional current.
I didn't change anything between problem one, problem two. I'm just replacing the new sense mode displacement. 0.423 micrometers.
So I have let me show you what I did, and maybe this will make sense to you. My motional current equation is exactly the same, but instead of using ds naught, I'm using ds, where ds is ds naught minus that equilibrium displacement, because I'm saying the plates are now closer than they were together.
And using your initial excess from that we calculated before, or the magnitude of that. So you're doing
Right, which is going to be, that value is actually going to change slightly for the second iteration.
Thank you. That I was misunderstanding what value. I was thinking this new XS is no, we're putting it in here to magnitude of excess.
Right, but that isn't XS.
No, it's not. It's not the sense mode displacement. It's your new
Equilibrium displacement for your,
thank you.
yeah.
I wasn't asking the right
There's
question.
so many different little.
If I see something that doesn't have a subscript on it, I know I'm doing something somewhere. I'm a stickler for having all little pieces of information.
Yeah.
This stuff throughout.
So just for people in Zoom land, this is the thing we're having. XD represents the drive mode displacement due to AC actuation force.
That dramatically changed my result.
Did it really?
Yeah, because what I was doing was thinking, okay, the displacement isn't changing. We're not taking that the thing a little bit further. No, I misunderstood what was being calculated. I wasn't thinking this is our new equilibrium position because of pull-in. I was thinking, no, it's just the pull-in's taking it from whatever where displacement is to a little bit further. So I did that wrong. So I replaced my initial distance.
Okay, it took me a second to process here.
DS is equal to DS of naught minus the new calculated position, and then you're taking your original excess value and then same equation as before. So that takes it from like 180 to 590. Really?
Well, it should make it stronger because now the variations are relatively larger because the gap is smaller.
Yeah, that's just, it's larger than what I expected to increase by.
Well, 590 times 10 to the negative 12 is still.
Well, I mean, it's still small, but you know, it's.
Thank you. I just wasn't asking the question. Of that.
Probably doesn't help that XS and X naught are both in the Z direction
No, I mean,
for this particular system.
why would you choose this degree?
So I believe that the motional current in problem 2 should be larger than the motional current observed in problem 1.
That makes sense.
Yeah.
Sometimes I have to just like sit back and double check. It's like, does this even make any sense?
Yeah.
I just don't know the basic principles.
Yeah, so I'm seeing 372 times 10 to the negative 12 amps on problem 1, and then 590 times 10 to the negative 12 amps on problem 2.
Okay.
Both significantly higher than
Yeah.
the. For part 1.
Yeah, and then for problem 3, you're just figuring out what value of omega makes the total displacement. And so by that, I mean the displacement due to pull-in forces and the displacement due to the presence of a Coriolis force summed together to make 1.667 microns, which is exactly 1/3 of the nominal gap.
So the way I did that, now that you mentioned, I probably did that wrong.
Although actually, so now that I think about that though, technically speaking, so let me think about this real quick, because we're just saying arbitrarily that if we exceed.
We did this at some point. On that rotation. No.
I don't recall. That would have been helpful. So the way I did it is I took the equation for our sense mode displacement, rearranged that to solve for what our, I'm sorry, I'm blanking on the name for omega now.
Capital omega is the rotation that we're sensing.
Thank you, our rotation. The only value that's changing here is XS, that everything else is a constant that we've been given.
Right.
The excess I used, which I now know is incorrect, was just 0.423 micrometers, basically our new pull-in effect.
Right.
Distance.
So what I'm trying to get at here is that the pull-in effect plus the displacement caused by a Coriolis force at some point will be large enough to cause our plates to snap together for a particular rotational threshold. So we got to figure out what that
threshold
is.
Yeah, okay.
Right. And I didn't ask you to solve for it for effectively the problem 1 condition where we're not worrying about the electrostatic attraction, but obviously that rotational threshold would be much lower because we're not already making up some portion of that gap with the electrostatic attraction. I guess one way to think about this would be to figure out. You know, you've only got 5 volts DC on this system, right? So consider 5 volts to be your pull-in voltage. What does the gap need to be to satisfy that constraint? And then figure out what sense mode displacement gives you. Or sense mode displacement plus the pull-in displacement that we already have observed. Causes the plates to collapse.
I'm not sure I'm exactly following this correctly. So to me, unless I'm misunderstanding, the pull-in point, it's past this point that you actually get the 2 parallel plate capacitors snapping together.
Correct.
Okay, and that's DSO over 3, 1.66 micrometers.
Right.
Well, if I'm taking 5 volts, that's our bias voltage,
Mhm.
and I'm taking our equation for pull-in voltage, just saying 5 volts is our pull-in. Rearranging this to solve for DSO, I'm getting that the new DSO is, okay, well, hold on, that's 4.889 micrometers, so that's just that offset.
Mhm.
Okay, so that gives me that, that's less than the 5 that it begins with, so that's something.
Yeah.
Okay.
So this is me. Yeah, I mean, the 5 volts potential difference is what's going to cause the plates to snap together. Right. And we know that the plates will snap together. So let me write some things here, right? So we know that our pull-in voltage VP is √8 over 27. K, this will be cents something, and then there's a D cubed in the denominator, right? Or is it KD cubed over something?
The way I've got this written out is I use the simplified form of 2 DSO over 3 times the root KS over 1.5 C pi. So I'm using a much more simplified version. Maybe just.
I've got I might have what you just said. 'Cause I can look it up. I've got like K total times E cubed over epsilon. Times.
Maybe got other notes.
Which, by the way, I definitely couldn't find in my notes, and I had to Google. Calculate the voltage. I'm assuming. Well, I don't know, like I went back and watched lectures, but look at this stuff somewhere. So are you just using this
I'm failing to, I don't know, if I can't get my brain to make the connection here. So the equation I have for,
Using this equation. Well, these are functions of mass.
no, the equation I'm using for XS is the matched mode equation, which is XS equals,
Let's put this.
XS is -2 MD over MS time quantity times XD times your Coriolis force radial, whatever, QS over omega naught S.
I think that's like an expanded version of that for that problem. So you're talking about, that's separated.
Yeah, we separated out.
So you
based
are
on
using,
position.
you are using that one.
Yeah, I'm using that formula.
Okay.
Then I rearrange that form.
We don't have mass stuff there.
Huh?
We don't have mass.
Yeah, we do. It's in the problem description.
Oh, okay.
Yeah, so we're given that. Right in here. Yeah, MD and MS.
Oh, okay.
So we are given the mass. And
And
then,
then you just solve for capital omega.
right, I'm just solving for capital omega. The problem is trying to make sure I understand what he was describing, which is,
You definitely shouldn't be getting meters per second.
no, I should be getting radians per second, but mine.
It should be like 1/seconds or something.
It doesn't like that.
Yeah, it does know what radian is, but it does calculate things. Oh. You okay?
I just put the back of the chair on my heel and my tendonitis is flaring up, so that hurt a whole lot. Okay.
I want to make sure.
So this is the equation for pull-in voltage, but now that I'm thinking about things, I'm having trouble in my head with kind of a chicken and egg situation here, right? So what I did originally is I said, all right, so DS naught or D naught S or whatever the hell I called it is 5 microns, which means if my total Z displacement is greater than or equal to 1.667 microns, my plates will snap together. That total displacement is my equilibrium displacement, which is effectively fixed by my DC biasing voltage, plus the magnitude of my sense mode displacement. So I need to figure out what omega value makes SS big enough such that the total displacement is 1.667 volts. Does that make sense?
Yeah.
Okay.
I just.
Yeah, let's stick with that.
Together what you were saying earlier, I was like, I thought I was thinking the right thing, but anyway. Round and round, yes. And we can do that pretty simply just by solving with the excess as a function of frequency equals the negative.
Yep.
Mass fractional, all that.
Mhm.
Which I completely forgotten how to properly use the solve for functions in math code, so I end up rewriting your thing every time.
Well, I completely forgot about the salt box until you mentioned it. Atari would not have to be able to use that access. I had to go back and figure out a new method for that, but essentially. What I did here, Dr. Hartman, was just rewrite this equation and then. My X naught calculated from the previous step, took the magnitude XS, and then. Of course, that should be in radians per second, that's in meters per second, because math cat's being weird. I could be grossly misunderstanding what you're meaning by this.
So that's Where's XD?
There's your meter. There's your
There's my meters, that's why it was gone. Yeah, I rewrote that and forgot that, let me.
Yeah. Cause that rotational rate seems
No.
so small
Let me-
that pull-in should be occurring with the rotational speed that I give you in the problem statement, which should not be true.
I'm working so hard. When we get done with presentations, I want to be done.
So then I am saying, I'll just put it up here, right? So XS is -2 MD over MS times XD times capital Omega times US over Omega naught S. And we have some target value in mind here because we know what X naught is. So rearranging this Omega would be
XS times MS times.
XS over XD times MS over MD times Omega naught S over QS times -1/2. Because all of these things are known.
And our X naught is what we're calculating from our.
So X naught is the equilibrium displacement caused by the 5-volt
DC, okay.
Yes.
That's, yeah, had to make sure that I write that down.
Okay, now I'm getting -1.704 with a 90-degree angle on it. In subseconds, so that took care of the. Which is significantly larger than what I was getting before.
Right, so it should be greater than 1 radian per second, or again, we're hitting pull in when we just,
Turn it on.
yeah. Or we were hitting pull in at the beginning, we somehow didn't realize it, but we know that shouldn't be true.
Right. Does that kind of sound 1.7?
Yeah, I mean, there's. I have it as 4, but again, there are a couple of mistakes in my thing. So I could very much see why it would be in the ballpark of 2.
I'll just write out these values for you to give you an idea. Where we are in the neighborhood here.
So I don't. I know that I asked you to do this, but I no longer agree with that bit, so.
Let me remove it, but don't confuse myself then.
Yes.
I'm gonna see that and go, what is this about?
So if we know that our total displacement is 1.667 microns, that's the maximum displacement in the Z direction that we can have.
And we're less than that here with
So I would say. So do like 1.667 microns minus X naught, or what I'm calling X naught, the equilibrium displacement. Okay. And just put that there, save that as XS prime or some such nonsense, or SX max, or. And then replace that with SX max and just see. Yeah, that's what I would expect,
Okay, so I was,
which is exactly half of what I was getting here, which is because I forgot a factor of 2 earlier on.
okay, so I just went a little bit off. You're saying, okay, what our new displacement is, and then plus the displacement calculated before, when it should just be what our maximum could be minus that.
Yeah.
Okay. Thank you. That. There are definitely some leaps here that in my sleep deprived brain, I don't think I would have made.
And then like, yeah, this should be straightforward, goes to do it like.
I'm gonna say homework, or take home exam 1. Initially looking at that, I was kind of spooked. Holy cow, there's so many parts of this, but then you break it down, it plays.
It actually would, and always have it.
And this, I was like, oh yeah, this is gonna be easy.
So it's the exact opposite thing.
Yep.
I
Okay.
just love when I look at stuff, I'm like, oh, this equation should work, and I go to look at it. I'm like, I don't think this is right. This works. It's not worth sitting stressing over and just be like, hey, how does this work? Oh. Oh, I've been asked to ask you, were we doing presentation?
105.
That's the same as last.
Had to remember, that's your capstone stuff. I was
Yeah.
thinking,
Yeah.
oh my gosh.
We have presentations.
Nope, nothing for you, Steve. All right, you guys got anything else for me?
I think you answered in obnoxious detail. Not to say that my questions. I think the only other obnoxious question I have to ask is concerning homeworks. I realized looking back at them, I submitted a couple where the units weren't exactly. It was just it was exactly written out what I plugged into MathCAD. So I have centimeters and then I have meters.
It's fine, I can figure that out.
Okay.
No big deal.
Probably gonna look at your timelines, feel like maybe.
Yes. No, I understand that, a meter is 100 centimeters, is 1,000,000 microns, is a blah, blah, blah.
It's just one.
I can always go on my MathCAD sheet and just tell it, hey, give me the units that Steven had. Is the thing the same? Yep, okay.
Which is drastically different than how it's drilled in our heads, but it was like the 240s math classes. And some of them are very strict on, oh, you gotta carry this all. Hey,
No, I mean,
I get it.
this isn't web work where it's specifically telling you this is the unit for this problem. Yeah, so I will use my knowledge of engineering units as is necessary.
Yeah, all the numbers are there, powers of 10 are kind of different, the decimal in a different place, all accepted. Well, that has definitely been me in the button before, I got like 12, which is 10.2 or something, but.
Remember that one work was the only ones. They had a box learning. I think when I was at ETBU, I had to use that one. It didn't have the unit sensitivity that WebWork does, but because it runs through the browser like WebWork, but for whatever reason, it constantly made my computer want to shut down the browser and then restart the interface. So I don't know what trash.
So for web work, the units are a user defined thing. So whoever wrote the problem said the final answer should be in this specific unit. The sensitivity is also can be set, I think, for the class as a whole for the assignment. And I think sometimes even just a specific problem of like, usually it's set to like 1%, but
Which 1%? I mean, that can be a big.
exactly. And then so for some things like it's set like 0.01%, and it just means like, oh, if you don't use a computer or store
Yeah.
variables, you're never going to get this corrected.
There was, it might have been for circuits, but it very well could have been a 240 class. Ended up having to go with MathPad, and I just kept clicking the, like, show me more, higher accurate
Mhm.
thing. And I got up to like 9 after the decimal, and that's what it took to make it work. I'm like, this is wrong.
Yeah.
Not right.
Yeah.
They ended up changing it, but it's like,
There were some questions like that, yeah, in one of the web works for one of the EE classes that I just finally was like, this is completely asinine. So I went through and learned how to change the tolerance. to be like 0.1% seems way more than accurate as necessary and would not make you have to put in 12 decimals.
Yeah. I mean, 0.01% on when your answer is already very small is way more difficult than when your
Yeah.
answer is like, oh, 10 to the fifth.
Yep. All right.
I haven't. 24 hours.
Yep, I'm gonna go get some lunch as well.
Friends drove me to CC's pizza yesterday. Which was surpassed my expectations.
See, is that the buffet?
Yeah.
Oh, okay, yeah,
Yeah, I'll try to get these uploaded soon-ish, Hannah.
I like CC's, it's really, it's got a variety going